Hello, this is part 14 of a series of videos about parametric curves. We've been using Mathematica, this program that you see is Mathematica, to work at developing visuals and calculus tools to help us understand these curves and the motion that they model. And we've been starting to focus in on the calculus tools, and even though this is going to involve calculus, I want you to know that pre-calculus students are certainly welcome and encouraged to continue watching these videos. I am going to try to develop the calculus tools from a very intuitive, physical, geometric standpoint, so hopefully you will still benefit from this. I am interested in ultimately getting toward curved motion, but we still need to continue for at least a few more videos on straight line motion, though at a non-constant speed. So what we did in the last video is we used Mathematica to illustrate that the outputs of the speed function of the motion give the slopes of the distance traveled function. That's the key mathematical concept and physical concept to realize here. Here is the situation. Pause the video, read this over if you haven't before. In this video I'm going to use a lot of Mathematica code to try to understand what's going on here. You're definitely going to be lost if you don't watch the previous videos, so watch the previous videos to make sure you understand what's going on here. Just to summarize the very end of the last video, this was an example where we were looking at motion along a straight line that was not at a constant speed, and these two graphs were the key things we were looking at. This blue graph was showing how the distance traveled so far depends on time. It has to increase in value if you are moving. Because it increases fairly rapidly at first, the slope is fairly steep here at first, relatively speaking. That means it's moving fairly fast at first, but then it slows down in here because the slope gets smaller. In fact, at this instant in time, time equals 0.5, the slope is 0, so it's like there's a pause for one instant in time, and then it gets back up to a higher slope, and so the object is speeding up again as it moves along a straight line. The red graph is the actual speed. The blue graph is in meters, the red graph is in meters per second. It starts out up at 15 meters per second, decreases in value to 0 for one instant in time, then increases in value to a speed of 15 meters a second again at time equals 1 second. And we use some numerical calculations in Mathematica to verify that the red graph, the outputs of the red graph, give you the slopes of the blue graph. I want to now use Mathematica to illustrate this in some more detail, and specifically I want to talk about the equation of something called the tangent line to the blue graph, the distance traveled graph, at any moment in time. I'll call it at an arbitrary moment in time, if I can spell time, t equals, slower than I'm typing here, t equals b is my arbitrary moment in time. You gotta recall the equation of a line. You can either write it in slope-intercept form or point-slope form, and the way I recommend thinking about things in point-slope form is like this. The y-coordinate as a variable here, this is going to be an equation relating two variables. Y is going to be the dependent variable and t is going to be the independent variable, is the slope times the independent variable minus a certain fixed point, first coordinate of a point on the line. I'll call it t sub 0 or t naught for short, plus the corresponding second coordinate of that same point on the line. Okay, so this equation is a form of the point-slope form of the equation of a line, and it should make sense because if you plug in t equals t naught, well, I guess I better use a b here, sorry about that, instead of a t naught. If you plug in t equals b, b minus b is 0, this goes away, and you get the second coordinate of the point when the first coordinate is b, and I'm calling that y sub 0. Maybe I should call it something else, but I'm calling it y sub 0. In our situation, because I said the speed gives you the slope, we can rewrite this as speed of b, speed of t is a function, so I'm plugging b into the speed function, multiply that by t minus b, And y sub 0, or y naught for short, I like that pun there, is the distance traveled at time b, dist of b. What I'm going to do now is I'm going to use Mathematica to create a command that's going to plot this line, this tangent line, at an arbitrary point whose first coordinate is b on the distance traveled graph. It's going to make an animation, ultimately. I'm going to use it to make an animation. Okay? Get that? The tangent line to the distance traveled graph at an arbitrary moment in time has that equation, and I'm going to think of this as a function of t involving a parameter b, an animation parameter really. I'll call it tangent plot. So again, this is a Mathematica command that I am creating here. It's going to be a regular plot of this function whose slope is speed of b. I've already defined the speed function. And whose first coordinate is b, and whose second coordinate is dist of b. I've already defined the distance traveled function. I'll plot this from 0 to 1. Let's add some options in here like plot style, thick maybe magenta, we could color it magenta. And we'll pick a plot range here, say 0 to 1, and for the horizontal distance, and 0 to 15 for the vertical window here. And that has now created a function that's going to take a numerical input, like say b equals 0.8, and return a graphical output. It's a line. I'm actually going to add a little bit more to this. I'm also going to use the show command along with ListPlot to plot the specific point that this is going to be the tangent line to the distance traveled graph at. Remember, ListPlot plots points. This is the syntax we want. The first coordinate, because the animation parameter is going to be b, will be b. And the second point will be dist of b. That'll be the second coordinate of the point. I'll add the option plot style black, comma, point size, 0.02 say. That's going to add a dot in the graph here. Yep, there it is. You see the dot there? The black dot. Alright, now we want to use this with an animation. I'm going to use, go back up here and copy and paste this code, which I used a few videos ago, down here. These are similar kinds of codes. I think I've already entered them, but just to make sure I'll enter them again. And I will put the tangent plot in here inside the manipulate in the grid. I think I'd like to add even more to the tangent plot. Let's put the distance traveled and speed graphs in here. So again, I told you I'm going to use Mathematica in a lot of detailed ways here very quickly. So if this is a problem for you, you want to go back and watch some old videos. Okay, yeah, that's what I want. You see the magenta line is in there. I'm going to combine these now. I'm also going to, I had a blank in the lower right corner. Remember, grid makes a grid of things, in this case graphs. I'm going to put this tangent plot in the lower right corner, and it's going to be part of the animation. B is the animation parameter. I picked a different h here. Let's go back to h equals. Let's go ahead and make it that other one. 4 times t minus 1/2 cubed plus 1/2. And let's see what happens here. You may have to zoom in to see this better. Make your video bigger. Okay. This is what I want. I only want b to go up to 1. About out of time for this video. I'm going to go ahead and let this run a little bit as I end the video. I want you to think about what's going on here in the context of what I mentioned in the previous videos. especially the last one and some other recent ones. In the next video I will come back to this and we'll try to focus on understanding it.